There we go. So, continue. All right, so now we're gonna do 27.4. And so any ideas on how to approach this problem for anybody, including you guys that are here? I mean, what's the first thing that we think when we're talking about acceleration? Yeah, I mean, as well. But what causes an acceleration? Like, exactly, force, right? So what kind of force is being applied in this particular problem here? What kind of force is happening?
Force on the magnetic field.
Exactly. Now, the equation for that is going to be this one. F equals, this is a vector, right? Q times B plus, where Q is equal to 1, 2 times 10 to the negative 8 coulombs. Velocity is a vector, right? So this is going to be 3.0 times 10 meters per second, J hat. Beautiful. Okay. Now, you guys remember how to do cross product? Yeah, the determinant way, yeah. So let's go ahead and do that. And we're given also, this is part A. This is part, we're given a magnetic field. Oh, yeah, make sure you guys have the different numbers, or I think we all have similar numbers. So plus 0. Okay. And we also given a mass, right? Yeah. All right, so we're gonna do this cross product. I hope you guys remember how to do those. So we're gonna say that F is equal Q I, and I don't have this. Wait, sorry. Size I, so is it V cross B? Now we're just gonna put in their number. So this is 0. 3.0 times 10 to the 4th J K. Jesus, my handwriting looks awful. It's fine. 3. Are you looking at this one here? Yeah. I'll do it this way. All right, so this is going to be 0, 0. All right, there we go. So once you solve this number, you're going to get a force, right? And I'm going to let you guys try to work this out. But when I did it, I got it to be, because I'm not going to do the math for you guys in this case. I'm just going to set up the problem for you. I got it to be this 6.8 times 10 to the negative 4 newtons. Now, what is the direction of this? Just by looking at the vectors. Just by looking at the vectors, can we figure out the direction? I mean, if you do the cross product, you will find out which vector, like in which direction it's going, right? But just by looking at it, like just trying to plot it in your head and try the cross product in your head. So, I and J have 0 components, right? So this is in the K hat direction, because that's going to be asked. This is the second part. This is part B. No, part B is the magnetic field. No, that's this one. Yeah, direction of acceleration. But they're asking for magnitude, if I'm not wrong. Yeah, magnitude of the acceleration. Now, we know that F is equal to ma as well. So A is going to be to the F over M. And this gave me, when I did this math, it gave me 0.33 meters per second squared. So this is my answer to my numbers. I don't know if we all have the same numbers, but this is basically the entirety of the problem. This is 27.4. So any questions with this problem? With part A at least? I don't know how to go back here from the board to see if someone is on the chat. Yeah, thank you. All right, no. Can you hit participants real quick? Just make sure everybody's here. All right, cool. Awesome. So since there are no questions, let's do one more. Let's do, I thought problem 2713 was oh, all right. So one more question. All right. So what is the direction of the acceleration, right? It's going to be along the force, right? So it's negative k hat in this case. So this is part B, and this is part A. There you go. All right. So since this is all recorded, you guys can see later. So I'm going to erase all of this. So start a new problem. Jesus, it's going to take forever. Here, clear all my. All right, there we go. Beautiful. All right, so now let's go over 2713. 2713, which can you pass a next one? I hope you guys are looking at it real quick. So we're given basically some, I don't know what's the name of this shape, right? It's like a triangle, like a, what is, it's not a parallelepiped. I don't know what it is. Well, we're given we're given a triangle with a piece of cake kind of shape, right? So I'm gonna try my best to draw this to the best of my abilities. Yeah, I wish I could use OneNote. I don't know why I cannot go back. And they didn't let me share it, but can I change the color? No, maybe. Oh, all right. So this goes something like this. This. There we go. Something like this. Right. So this is 30 centimeters. This is 40 centimeters. And the hypotenuse is 50 centimeters, right? Now, they're asking for flux, right? And we are also given a magnetic field that goes along the Z, and then this is Y, and this is X. So we're given a magnetic field that goes along the Z direction, right? Now, how do we approach this problem and what is flux? Let me just start by that. Let me ask someone, can someone answer what is flux? Because that's what they're asking. At least we need to know what is it that we're looking for, right?
Vector.
There we go. So in this case will be B because it's magnetic flux, right? So equals double. Is it a closed loop? No, it's single. Is B D A, right? Okay. Now, this right here, this is a dot product, right? So we can write this as double integral of B cosine theta dA. Beautiful. Now, B is constant because it doesn't depend on time. It's not pulsating or anything, right? So we can take it out. Cosine is constant as well, so we can take it out. So we're going to have This is just a long way of getting the the area, but it's good to do at least once. So dA, right? Now, what's going to be my dA in this case? Let's figure out like how do we set up the differential area here? We know the answer. We know it that is 30 in this case 30 times 30 centimeters, right? You know the answer. That's the area that is being hit by the magnetic field, right? But how do we prove that? Yeah, I'm trying to set up the double integral where dA, this is more like a little bit more math than physics in this case, because I just don't want to write the area of it, right? So what's dA in this case? In this case, what's differential area? I mean, you can ask and I will tell you, and then we can understand this, because this will be really important in sources of magnetic field and realizing what is dA, ds, dV, ds being the line integral, dV being the volume integral. So what is changing here? If I were to integrate this in this direction and then on this direction, I need to use OneNote. So it's going to be, right, it's going to be a rectangle, right? So it's going to be dx dy. So that's going to give me a little piece here, little small. And when I integrate, I'm going to sum all the little squares that are making this this face right here, right? So what? No, no, it's not, because you can have a sheet of paper that is you can have a sheet of paper like I'm putting it right now like this, right? And you can have a magnetic field that is going into it like this, and this is not a closed this is not closed surface. Mm-hmm. But the ones that are being hit in this case by the magnetic field, because we know that it's coming from the z direction, right? So dA is going to be dx dy. Beautiful. So we can keep on setting this integral. Just extra. This is not necessary, but I just want to see, guys, where this is coming from. All right. So we're going from 0 to 30 centimeters. 0 to 30 centimeters. This is dx dy. Beautiful. And now this is just the area. The integral of dx is x. The integral of dy is y. We put in the boundaries. It's going to be 30 times 30, and that's pretty much it. But I just want to show you guys, instead of just telling you the area, just see where this is coming and why am I doing stuff. So flux is equal to b cosine theta of the area. Okay. Mm-hmm. And we're gonna go. Jesus, I don't. Oh, this is part B. This is part B, by the way. I skipped one step. This is part B. Then we're gonna do part A. Part B. And all right. And actually, let's answer part A real quick. What is A? Like, just by looking at it, we can know the answer. Because the magnetic field is coming this way along the z-axis, right? The area vector of this is in this direction. What's the angle between them? Right, cosine of 90 is 0. So anything multiplied by 0. So the first one, part A is 0. Okay, so A is 0. All right, so now we're gonna put in some numbers. So this is gonna be 0.18 Tesla. Area is gonna be 0.3 meters squared. And the cosine, what's my angle here? And what is this? I just said it. Like, the angle is theta represents the angle between the area vector of the surfaces being hit and the magnetic field, right? Now, where's my area vector in the surface BECF pointing at? between the X and Z. No, it's pointing in the Z direction, negative Z in this case, because if this is the, let's say we're looking at this side right here, this is the symbol for I. We're looking at this side, we're looking at, it's gonna be like a square, right? Now, a pointing vector that is coming at you is a dot, right? So this is how it looks from this perspective, because the area vector goes outwards from the surface, and this is just a convention. Like this is just the way it is. Like everybody decides that this is true, and that's it. But you can get the same magnitude if you flip it. So if my area vector is pointing outwards and my magnetic field is opposite to it, what's the angle between them? So you have something like this. This is a setup that you have. What's the angle here? Exactly. It's 180. So what's the cosine of 180? Absolutely. So I'm going to continue here. Beautiful. So boom, flux is equal to, in my case, it was negative 0.0152. And try that here. We have, yeah, I think we have the same numbers here. Negative 0. 0. Jesus. 1152. Why am I getting an O? Okay. There we go. So it was my answer, right? I just plug it in again and I got the right answer. Now, let's do part C real quick. And this is the one that took me a little bit longer to figure out, right? And I want to make sure you guys like ask questions about this, because if not, I'm just going to state it and I'm just going to move on with it. And that's pretty much it, because we have to look at it for a second here. And there's a little bit of geometry, or maybe there's another way that I haven't thought about this.
Yes, for that question on number C, I was confused a little bit on trying to detect the direction of the area vector. So
awesome.
on cosine, just wondering which, since it's cosine, why did we choose the perpendicular? Because the correct answer was, well, if we use the f over x axis, the area of x.
Yeah, the angle is the angle that you're gonna get is gonna be either cosine of, I think it's 3/5 or arctangent of 4/3. That's the angle. And I'm gonna show you the cosine one. I was not convinced by it, like, although it's true, like, because I prove it later, but I thought it was so complicated. And so I'm gonna do the way that I did it with arctangent. So this is going to be a top drawing of this piece of cake, right? So this is going to be something like this. So this is part B is the one that we just did, negative 1.15 times 10 to negative 2 Weber. This is the one that we did. And part A is 0. So let me just, you can ask the question if you want. If you have a question, you can ask us. So sorry. So it's gonna be
30, 40, 30, 40, 50.
All right. So
30.
This right here is the top view of our triangle, right? Where this is 30 centimeters and this is 40 centimeters, right? So the goal here is to find something like this, right? Because this is top view, so this will be my area vector, and the magnetic field will be somewhere here, right? Now, what I did was I find this theta right here. I'll go like this. Like this. Right? So we know that this theta right here is, and we have another angle here I'm gonna call alpha, right? So this becomes alpha, and this becomes theta, right? What I did was treat this as your adjacent, and then this as your opposite. And we can find that the angle there, tangent of theta, is going to be opposite over adjacent, right? Beautiful. And then your theta is going to be arctangent of 4/3 in this case, right? Is it clear now? I'm trying not to make it clear, so you guys ask me a question here. If this is clear, like arctangent of 4/3 is clear, then we just plug it in back and we're gonna get the same value because the total flux is 0 in this case. We're gonna prove it later. So part D is 0. I'm just giving you that little heads up. But now, does this make sense, this part right here?
Yeah, just why did we choose to use theta instead of alpha?
All right, see, this is the question that I'm looking for, right? So what is the definition of a dot product, right? It's the angle between the magnetic field and here. So it's this angle between them. Because this alpha is the angle between the x-axis, right?
Yeah.
So now you see it. That's the question that I was looking for. Because if I state this and I give you the answer, then we don't get anywhere, right? So, all right. So if this is clear, then we know we're just gonna. I'm not gonna do the double integral again, but we know where this is coming from. So flux B is going to be equal to the area times B times cosine of arctangent of 4/3. And I think this is the clearest way to see it. There's a way to do it with cosine, but I thought it was too tricky, so I decided to go this way. And when I did this, I got it to be, make sure you're using the right area, right? I'm gonna let you guys figure that out. You're using the right area. So it's gonna be, or you can ask me the question as well. So 1152 Web. There we go. My handwriting is not that terrible.
So just a quick question. I did the way of trying to fix it with the cosine, and but since cosine is always the adjacent, I tried to find the 40 centimeter over 50 centimeter, which should be the adjacent for the vector that sits parallel to the vector field, magnetic field, right?
I think so. I think you have to use the, wait, you have to find this one, this theta. You have to find theta in this case. So theta would be, it would be, if this is 50, just to answer a question real quick, if this is 50, then this will be cosine theta equals 5, Jesus. 3/5, and theta would be r cosine of 3/5. This is a little bit less intuitive, at least in my opinion. So like, because if I say this, then it's like, how do you know if theta is the angle between them? But here you can see how theta it is, like when you use the arctangent in this case.
Right. So, but the thing is, shouldn't we use the area vector that's parallel to the magnetic field, not the area vector that's perpendicular to the vector field? Because when I did the vector area that's perpendicular to the magnetic field, it's worked. But when I used the parallel, it did not work. And in the what we studied in the law, it says dot product takes the vector that's parallel to the magnetic field, right?
Well, not not parallel. Like most of the times, like there, all right, so let me see if this clears the question a little bit. There's no reason, there's no statement that says like, oh, it has to be. Like, no. The reason is that most of the surfaces, like this one, this is the area vector, right? And now you have a magnetic field coming in this way, area vector. These are parallel, right?
Right.
But I can flip this like this, right? And this, oh my God, sorry. I'm better in OneNote. Next one, I will try to figure out how to use OneNote and Zoom at the same time. All right. So this one, let's say this is like angle, right? So this goes like this. See? Like you can have this angle here,
Right.
and that's theta. The reason when it's perpendicular is 0. We just prove it in part A, because the area vector in this face of the cake is going this way. So the angle between the magnetic field and the area vector is 90 degrees, and cosine of 90 is 0. So that's why the first one is 0.
Right.
So does that clear your question?
Yeah. Thank you.
Undo. There we go. Oh, I got scared for a second. All right, awesome. So now this is part C of this question of the problem. I thought this was a really good one. It makes you think a little bit. It's not plug and chug. Now the part D is looking for the total flux, right? So the total flux, the total magnetic flux to be precise, is equal to flux 1 plus flux 2 is equal to 0. Since they're the same opposite sign, it's just 0. So D is 0. And I think that's what I got. Yeah. Can you try real quick? Just making sure I'm getting the right answers. Because I didn't plug the numbers, to be honest. I just saw. There we go. All right, beautiful. All right, so any questions about this problem? Especially, I know part A and B are easier, but any more questions about this? How do I find theta? I can explain it again if it didn't make sense, but I hope it's clear. All right. All right, so since there's no questions, let's do 2722, which I found was really good. I really like that problem. Let's do it. And I'm going to do that one and one more, and that's going to be then we're going to open up for questions, because in the end, this is your homework, right? But it's making sure you guys a little bit ahead. All right, now, I'm going to draw this, because I can draw that one. All right, so is everybody looking at the problems? Like, do you guys have it open in your computer? The ones that are on the meeting? Because there's people in here with me where I am, so just making sure you guys are also looking at the problems. Is that the case here? Yes, no, maybe. No. Well, I'm just gonna assume you guys are looking at the problem. So basically, in this case, you have a particle, a beam of protons, and it's doing this movement like this. All right. And in this area right here, we have a magnetic field. Oh, Jesus, what a drawing. Beautiful. All right, awesome. Now, we're told that the length that the beam of protons like crosses the magnetic field is 1.4 centimeters, 1.7 centimeters, 1.7 centimeters, and it has a velocity. For me, it was velocity. There's a velocity here. Make sure I'm trying to give you the best drawing I can. Kilometers per second. Awesome. Now, S is going to be this piece right here, this trajectory, all of this, right? Now, there's a couple ways of doing this problem, but I did it using arc length, right? And what equation do we have to use for this one? It's in the book. It's one of the barely is explained in the book is any clues on how to solve this problem? Set up the equation or even a question of why is this happening or well, the reason what we're not going to use that one is because you need an I, right? You need a current. So we don't have a current here. It's like what is an equation? The equation I'm looking for is like it's barely touched in class. They solve one problem. It's a cyclotron one. The cyclotron one, right? So that equation is given by, and I don't know how the yes. Yeah. So we're going to have MV over RQ. Beautiful. Now, the question is here, how do we find the radius of this? It's not S because I will write it as R, right? So how do we find this radius?
Is it gonna be four times the like circumference, the area that is cut? So we can get the circumference, then we get the radius.
Yes, that's a way to do it.
We have the arc length.
We have the, but like, you can do it that way, and you will get the same answer. You can find the perimeter, which is just a line, and you divide it by 4. You equal it to that, and that's completely fine. But the reason why I'm gonna do it this way is because your next chapter is chapter 28, which is sources of a magnetic field, and you guys are gonna start using arc length. So yeah, I just want you guys to see on how to set up the arc length because you guys are gonna use differential arc length. So just a little bit more familiar with that, but you're absolutely right, by the way. You can use that method as long as your algebra makes sense, you can do it because you can divide it by 4 and that's it. All right, so now arc length, oh no, sorry. What's the equation of arc length from Calc 1? Or is it Calc 1?
Yeah, we did one.
One. R is S equal R times what? Yeah, theta. Well, we're yeah, I see what you're saying, but we're gonna use that later, not today. But all right, so now my angle is this one right here, which is given by pi over 2. So S is equal to R pi over 2. Beautiful. I solve for R, so 2S over pi, and you should be getting this answer, which is almost, we're doing the same, but I just want to use arc length so you guys get used to using arc length. Because this moments you have to set up the integral in such a way you're going to give it a differential length, right? So when you do like I don't know, work, you have dx, right? So what is dx? You figure it out in physics 1. But here later we're going to solve a problem that is like a ring, and that is using differential arc length. So that's why I'm doing it, not to be like annoying or anything. I just want to make so next chapter you have this, right? So my R came to be 0.009 meters. This was what I got when I plugged all the numbers. Now we have everything basically because we know the mass of a proton is a constant, right? The charge of a proton is a constant, so both are given. We're given a velocity, right? So we can solve this problem now. So B is equal to the mass of the proton times meters per second over this 0.009 meters times the charge of the proton. Let's change like this. All right, so B for me was I didn't write the answer, so I have to plug it in. Well, if you do this, you're gonna get the right answer. And I don't know why. I think I just typed it in, but can you do this math real quick? Do you have the charge of a proton? Is 1.602 times to the negative 19, and the mass is 1.619 times to the negative 27. I think.
mass of a proton I usually do 1.67 times 10 to the negative
27, right?
27.
All right.
Charge of, oh, that's it.
The charge of a proton. Charge of a proton is the same as the charge of an electron. So it's the charge. It's the absolute value of the charge of an electron. So it's the same.
That's it, just 0.009 times.
Meter times this. This is meters.
1 2 kilometers a second. Left.
16.
1 2 3.
The 1.66 times 10 to the negative 6 Tesla. Let me see. I have this number here. Oh, here's my number. Here's my number. Wait, sorry guys. I got a different number. Yeah, something is wrong here. I don't know. I think that your charge is wrong. Is 1.6
Oh, 1.6.
1.6 times to the negative 19 the other way. So I found, there you go. There you go. That's the answer. So I got to be this 0.00196 Tesla.
So that's converting to meters per second.
Well, we just got to multiply by 1,000, right? That's what K stands for, right? All right. So this is my, any questions on this problem? Well, if
What did you get? So
all right, I'll let you do the math real quick.
I got 1.3 times 10 to the negative 3.
Should be fine. It's about the same.
I don't know if I did slightly different. No.
1 second.
Which is a pretty, I think it's a pretty normal magnetic field from what Dr. Fruit was saying.
I have a different radius, so.
At 1.5. I did my own calculation anyway, just to make sure. Okay, got it correct.
0.001.
Yeah, that correct check mark is pretty satisfying.
Yes.
It's like with diffy Qs and good job.
I didn't get a check mark. I do some.
This is the total calculation.
Okay, so
Make sure you have the right charge and mass exponents. So I get them mixed up from the time.
okay, so 0.015 minus just 0.
My brother was in geometry, so he was learning arc length. Not so long ago.
Oh. Wait, should I just get the same answer?
I have slightly different value
1.5. Oh, mine's
than you, I
1.7.
think. I think I have the same with him as him though.
Mhm.
This for velocity, I have 1.20 kilometers per second.
So you guys got the answer? You plug it in?
Yeah,
All right, you got it right?
yeah, I got it.
All right, awesome. All right, so let's do one more. Let's do one more. Let's do 2725, which is physics 1. All right, let's can you pass the problem real quick? 2725. All right, so 180 volts batteries connected across 2 parallel plates of area, some bend and separation, some bend. A beam of alpha particles of charged 2 electrons, twice the charge of electron, mass of this, is accelerated from rest through a potential difference of 1.7 kilovolts and enters the region between the plates perpendicular to the electric field as shown. Okay, so how do we even start this problem? And without not the constants, but what do we know that is happening to the alpha particles? And
It's going to a capacitor,
right,
and then
sort of.
And then there will be like positive, negative field, so the charged particle will.
Yes, but before that, it's accelerated through a potential difference, right?
Mhm.
So this looks a lot like a gravitational potential, right? Kind of the same set of physics too, where you drop something or something is from rest and it gains some energy, right? Because the particle is going from 0 to V and is gaining energy from somewhere, right? So we're gonna use conservation of energy to first find the velocity because we don't have it, right? Because they're asking for magnetic field, right? And the force that the electric field is applying to the particle has to be the same as the force applied by the magnetic field. So that's the whole purpose of this. So first, I'm gonna write the steps real quick. So first, we're gonna find V. Then we're gonna find FE, and then we're gonna find B. There we go. I think those are the steps. If not, we'll see how it goes. Awesome. So I'm gonna set up this equation. We hope this looks familiar. I really hope so. So mv1 squared plus qu1 plus one. Sorry, this is equal
QV1.
u1. Sorry,
Oh, Q1.
u1. Sorry, it's the same v. The thing is, like, one is velocity, one is v. Yeah, I'm gonna do some. Let me. There we go. This is voltage for us in this case, right? V1. So this is 1/2 mv2 squared plus the charge of the alpha particle v2.
And the QV1 is the same thing as KQ1, Q2 over R.
Exactly.
Okay.
That's potential. That's why I'm saying, like, this is a physics problem in a sense, right? So what is V1?
Sorry, I'm writing it.
Don't worry about it.
Is 0 because accelerated from the rest.
Absolutely. Now, we don't know what is a voltage 1 and voltage 2, but we know they're different, right? So K is going to be equal, subtracting KV2 from the right side of the equation. We're going to have that delta V is equal to 1/2 mv2 squared. Now I solve for this one for velocity. So V2 is equal to twice Q delta V over M square root. There we go.
Was there a particular reason that you wrote it as QV1 instead of like the other one? So you could write the Q delta V?
Well, I'll just skip one step, but because it would be 1/2 mv1 plus u1, right? And then, but we know what u1 and u2 are, right? We know that it's going to be q times v, right? So I just skipped that step, but yeah, you're absolutely right. This is u1, and then this is u2, just like a gravitational potential, right? I just skipped that step and put it what it was, because we know that the potential energy is coming from the voltage, right?
The running stuff, like you can write 1/2 mv squared is like, and what was it? It's like Dr. Hughes, he just added an extra mass on the bottom. He wrote it a different way.
Yeah, I mean, as long as you can divide everything by m, and you can, it's gonna still be the same thing. But here, I don't think I solved entirely here. There we go. So I don't know. I don't have this number, right? So here you have to plug in your numbers, right? And you are given the charge of the alpha particle, right? Which is 2 protons. And I think so. It's 2 protons, I think so. Momentum square. It's the same thing. It's the same thing.
I'm just trying to like visualize.
I just use this way is because it's physics 1, because you guys already did it. You solve it by units, like equal them to each other, and you will see. All right, so once we have this number, I'm gonna do it real quick as well. Let's plug in some numbers and figure out what is it, each velocity for each one. So we know that this is 1.1775. Let me know what you get, and then I just say that that's what I got.
The VSD potential difference, right?
That one, yeah, 1.7 kV. Sure. All right, so I'm plugging in the numbers right now. And then this is 1.7 times 10 to the 3 times 2 times 1.62 times 10 to the negative 19 over 6.64 times 10 to the negative 27, and the one on the top is multiplied by 2 again.
Mhm.
What do you got?
I got 41.700.
Yeah, I got the same 141.
Multiply the charge by 2.
Yeah, because that's the charge of an alpha particle. Damn, this is going super fast. Well, we're gonna go with that number. I think it has to be right because I already solved it. All right, so this is gonna be 41,000 meters per second. 41 kilometers per second. Jesus.
4.1 times 10 to the 5. Yep.
I got 5.8 times 10 to the 7. I think I had slightly different. Oh. I used the wrong mass.
All right, so we will figure out if this is right or not in a second. Meters per second. Now, we know that the electric field is going to be V over distance, right? Or we can use the capacitor equation as well. But since we know that the plates are going to be 100 volts from each other, so we can say that E is just going to be the voltage between them over the distance, which is 9.2 times 10 to the negative 3 meters. So this is 180 volts, 9.2 times 10 to the negative meters. So E E is going to be equal to
Is 2 times 2 times the charge of the proton times the velocity.
I think I know.
per meter. Awesome. Now, we know that the electric force is going to be equal to E times Q, right? But this force must be equal to the magnetic force, right? In order for the particle not to be like his path not to be affected by it, right? So we know that the magnetic force is going to be B cross B times Q, right? But in this case, the velocity and the magnetic field are perpendicular to each other, right? Perpendicular to each other. So that's going to be B cross B, B times B sine theta. And sine is theta is going to be 90, right? So it's going to be 1 and times Q. So we can cancel all the Q's here. And we will find that B is going to be equal to the electric field over the velocity. And then this is equal to, in this case, what number you got for electric?
I got the same one, 1.95.
All right, awesome. So divide that by the velocity. One shouldn't be that big. My Tesla is a huge unit, so
We saw that.
0.27.
So
Uh-huh.
This is a small number for the. Oh, no, I get a big number.
It has to be kind of big. All right. There we go. So the answer that we got, because what's her name? Herschel and I, we have the same numbers. So we got this. You're Christian, right? There you go. There we go. All right. So this is the answer for part A. Right here is verified. We did it. Now, part B is asking for the direction of this magnetic field. Can someone tell me the direction by using your hand rule?
it goes.
So
Oh. We found that.
We're looking for the.
I'm looking for the direction of the magnetic fields, right? So let's look at this real quick, right? I'm not going to tell you the answer yet, but if you ask me a question, we'll get there, right? So this at the plate, right? So we have, oh my goodness, I need to learn how to draw. All right, I'm gonna try this. Why not? So here, sorry for that. There you go. Boom, boom. Let's imagine all of them are parallel, right? Give me 1 second. I'll tell you right now. This is the capacitor. This is electric field, right? This will be my particle, right? So let me keep drawing here real quick. So here's my alpha particle. This is E, right? Fe goes in the same direction. The electric force goes in the same direction as the electric field, right? Because this Fe is just E times, the charge times the electric field, right? We know that by Coulomb's law, this is true. E charge times electric field, right? It's because those are the units, right? Electric field is Q squared over, Q over R squared times K, and Coulomb's law is Q squared over R squared times K, right? So we're missing a Q here. So this is true for Fe. And we know it's pointing downwards, right? So it's a negative K hat in this direction, right? Now, I need a magnetic field that makes a force in the upwards direction in K, right? So if the velocity is going in this direction, right? And we use the right hand rule, right? How do I get the magnetic field to point upwards? The magnetic force to point upwards in this case.
Yeah,
Out of the page, right? Yeah. So the magnetic field, if you look at this, right? Let's say the magnetic field has to be, this is the velocity. This will be the magnetic field. This is out of the page, by the way. Can you just not draw three-dimensional? This is it, right? This will give you a magnetic field. A force that points upwards. So if you put out of the page, should be the answer, because I haven't finished this problem yet. Right, there we go. So those are like the three main problems. And let's look at the next one real quick. Let's
Just
look at go ahead.
on the electric field, isn't it on the question showing going upward, since the positive plate is the lower one and the upper one is a negative plate?
Give me a second. Let me look at the drawing because I passed it. In this case, let me see the magnetic field. I swear to God, I saw this drawing differently. Give me a second. Give me a second.
Oh,
Give me a second. Oh, you're absolutely right. The plates are the opposite. I thought it was positive. Give me a second. The same logic will apply, but in this case, hey, Jesus, why is it working then?
Oh, well, should it be into the page? If velocity and
Maybe the force direction? How can we detect the force direction?
No, this is no, because we got the right answer. So give me 1 second real quick.
Sure.
Give me a second, because we got the right answer. And just maybe the charge is going from negative to positive here. Let me see. Let me see how capacitor. Let me look at the drawing of a capacitor real quick. No, we don't have to. Give me a second, because I definitely saw the diagram different. I saw it flipped. Is these particles?
times 10 to the 4. That's for electric field. It's just 10 to the 4 because it's 20 meters.
yeah. After that, you just divide that over distance, which is 9.2.
Give me a second, because I don't know I'm getting the right answer. Because you're right. The electric field goes from positive to negative, right? In this case.
The other question is, how can we detect the force? Because maybe the force is the one that it's inverted, which made the answer correct.
I'm thinking about how to invert the force here, but let me see. Is this positive? I don't know. Give me 1 little second here to see the electric field diagram, because it's going from positive to negative electric field of a capacitor. Give me a second. Yeah, it goes from positive to negative.
Yeah.
V over D, and then this is going downwards, and the particles are positively charged, so they're going along the line. They're not going against the lines. Give me a second. V cross V.
Or maybe because they're positive, so it will tend to go upward because of the negative plate is upward, and then the velocity is as its direction to the right, which kind of gives us, as you mentioned, the fundamental ideas. Magnetic field.
One voltage, that's another voltage. Right?
But remember, the magnetic field is pointing out of the page, not.
Yeah,
no.
because the force gonna still be upward because it's a positive particle.
Yeah.
The question, and the negative plate is gonna be upward. Oh no, wait. I'm confused. Yeah, the negative plate is upward.
Yeah.
Give me 1 second so I can. Let me do some math real quick in my head. Yeah, let me stop the recording for a second. Let me figure this out real quick so I can explain it, just in case. All right, there we go. After talking for a bit, figure this out. So let me redraw this real quick. All right, there we go. All right, so in the first time I did the problem, I had mixed the velocity and the magnetic field. I mixed them, and I realized that I also had the electric field pointing the opposite direction. I just saw the drawing in the wrong way, but we realized that, so that's fine. So let me do the drawing one more time here. There we go. All right, so let's do it one more time here. So here, so the electric field goes like this, right? Do we agree on this one this time? Yep.
Yep.
Beautiful. All right, there we go. So here we have the velocity going this direction. And now, yeah. Okay, good. There we go. Drawing. There we go. So this is E, right? And if E goes in the same direction, right? They go in the same direction. They're parallel to each other. Now, the velocity, if we do this drawing like this, we do this, boom, this is velocity, right? And this is V. The cross product goes down in here because I had a mix. So that was my issue here. I had it flipped. So this goes here. If you do right hand rule with this, if you turn your hand and you close it, or if you do the 3-finger method, you get the magnetic field is pointing downwards in this case. And I just had it flipped. Mine. Didn't realize the drawing was flipped, but that's fine. There we go. Minus, no, sorry. Minus. There we go. So is this clear now? Why is it pointing downwards?
Yeah, well, why is it pointing downwards?
Oh, because if you do the right hand rule with these two right here, B, little v and big B, if you do it, the vector is going to be pointing downwards.
Right, but we don't know the magnetic field vector.
But we need this to be downwards.
Why?
Because if you look at the problem, the problem is asking how do this particle gets in here, accelerates all over, and it is unaffected, right?
Okay, I see.
So unaffected means no acceleration. If you have no acceleration, it means that the sum of the forces is 0.
Yeah, thank you.
All right, there we go. So is it now clear? Yeah. Sorry for that, guys. I didn't realize the drawing was flipped. But that's why we look at the math and trying to figure it out. There we go. All right. So is this clear now? Hope it is. And any questions for what we have done so far? Because this is the last. What you put? Got you. Give me a second. All right. All right, got you. I got you. Don't worry about it. All right, so this is gonna be it for the Zoom meeting because it's 1 o'clock. Sorry, guys, I owe you 15 minutes. So that's why I went over and did a little bit of homework for you guys. But yeah, I hope you guys found this useful, like me explaining the homework. And if you have questions, I saw the homework. I saw the entire homework, and there's one question that I think it's one of the last ones. You have like a wire and a magnetic field, and you have a resistance and whatnot. And I thought if you guys need help with that problem, you can ask me as well. That took me a little bit, which is problem 2731. That one took me a little bit, but it's not bad. But if you guys need help with it, just send me an email and or send me on Canvas or whatever. I can help you out. It's not a problem. And all right, so this is gonna be it for today, and I'm gonna upload this to the YouTube channel. If you guys watch it or not, and later today is gonna be uploaded like by 4 o'clock. So any questions, any comments, anything? Let me go. All right. How do you say your name? Fahad?
Yes, it's bad.
Fahad. All right. So I hope you find it useful because the Harshila and Christian are here with me next to me. So